in this particular demonstration, we'll be showing the IMD performance of the vector signal analyzer. Basically, the equipment setup that we're going to be using for the demonstrations is shown in block diagram on screen right now. So basically what we have are two M9381A vector signal generators, each going through an isolator and then into a power combiner, and then the output of the power combiner is going into the M9393A vector signal analyzer. And the vector signal analyzer is being controlled and the data being displayed by the 89601B-SSA, SSA meaning Stepped Spectrum Analysis. The purpose of the isolators is to minimize the effects of the two sources beating against each other. Particularly problematic can be the ALCs of the two sources. So one source sees the power coming in from the other source, and then its ALC tries to compensate for that, and that can create some additional distortions. And what we're trying to do is demonstrate the distortion of the analyzer itself, so we want to try to minimize as much as possible any inherent distortion in the measurement setup itself. So that's the reason for the isolators. So with that, I'll now switch to the demo screen and actually show the equipment running. So now basically what we have going in are two tones that at the input to the analyzer are each at about 0 dBm. And basically what I've done is I've set the power of the individual sources in order to compensate for the loss through the system, in order for each of the sources to be at very close to 0 dBm going into the input of the analyzer. So what you see on screen right now is the soft front panels on the left for each of the two sources. So basically I have one of the sources tuned to 2.167 gigahertz and the other source 6 megahertz lower at 2.161 gigahertz. And then the loss through the different paths is slightly different, so I have the power set accordingly and have adjusted those in order to get the power at the input to the analyzer at 0 dBm for each of the tones. And you can see I have marker 1 and marker 2 at the peaks of those tones, and down here at the bottom of the screen you can see where the power level of each of those tones is at about 0 dBm. Additionally, what I've done is I've set the range, which is in some analyzers would often be referred to as the reference level. The terminology that we use in our vector signal analyzer is range. So that range is set to plus 15 dBm, which is actually somewhat above the actual total input power of the two tones combined, which is roughly around plus 6 dBm. One of the features of the Stepped Spectrum Analysis capability of the 89601 software is that I can actually decouple the range setting from the top of display setting. So my top of display is actually at minus 10 dBm, and so the tops of both of the tones are actually off screen. And I've done this in order for us to be able to see the noise down here, because one of the things I want you to notice is the effective dynamic range that we have on screen right now is exceptional. So each of the tones is at 0 dBm, and you can see down here that the actual displayed noise level is around minus 100 dBm. The combination of the speed of the M9393 analyzer and the SSA software provides for the capability to run at very narrow resolution bandwidths and still have very responsive update rates in terms of spectrum display. So what you're looking at is a 50 megahertz span with a 300 hertz resolution bandwidth. That gives us a displayed noise floor of around minus 100 dBm, but still, even with the narrow res bandwidth, a very responsive update rate. You can see it's updating at multiple times a second, and in fact, there's an estimated spectral rate, so you can see even in a 300 hertz res bandwidth that it's updating a spectrum rate of over 200 megahertz per second. So very responsive. Now, the critical point that we're trying to make in this particular demonstration is the intermod performance of the analyzer. So you can see we've got the two tones going in at 0 dBm. Those are these two markers here. And now we have a delta marker on the largest intermod distortion product. And you can see that that product is down minus 81 dB. Given that that the input signals are at 0 dBm, that makes the math pretty easy. So we can effectively just divide by 2 and say effectively what we're showing here is roughly, under these conditions, a plus 40 dBm TOI. So very impressive. Again, that is based on the a range setting of 15 dBm and the two input signals each at 0 dBm. So that's the primary portion of the demo that I wanted to show for today. Thank you.